Hello friends, I am Engineer Nasir. In this video, we will do a sample calculation to calculate the duct external static pressure. And in this study, we will follow tables and charts given in ASHRAE. For our sample calculation, we have a supply duct drawing. Duct size is 850 by 400 and airflow in this duct is 2000 liter per second. Then we have a branch from this duct. After the branch, the duct reduces to 850 by 300 and airflow value remains 1500 liter per second. We have duct fitting 45-degree elbow, 90-degree and transition piece. Now we will do the sample calculation for pressure drop. To calculate the pressure drop inside a fitting, we use this formula: total pressure drop equal to fitting loss coefficient into velocity pressure. Fitting loss coefficient we will select from the ASHRAE tables, and to calculate the velocity pressure we will use this formula. If velocity is in FPM, then we use this formula, and if velocity is in meters per second, then we use this formula. To calculate the total pressure drop inside a straight duct, we use this formula: total pressure drop equal to total straight duct length into friction loss rate. First, we will make a table of all fittings in this duct and straight duct with their length. We have a straight duct size 850 by 400 mm, length 82 linear meter, and airflow in this duct is 2000 liter per second. Then after transition, the duct size became 850 by 300 mm, its length is 3 linear meter, and airflow reduced to 1500 liter per second. We have one 90-degree elbow, size 850 by 400 mm, and airflow in this inside this also 2000 liter per second. Then we have one 45-degree also same size, and one transition piece 850 into 400 to 850 into 300, and we have one piece for it also. To calculate the pressure drop inside fitting, first we will select the fitting loss coefficient from the ASHRAE tables. If we have duct elbow without vanes, then we will select the fitting loss coefficient from this table. If our duct elbow is with vanes, then we use this table to select the fitting loss coefficient for it. For our sample calculation, we assume that we have a duct elbow with vanes, so we will use this table to select the fitting loss coefficient for it. And to select the fitting loss coefficient, we need to know two values, h by w and r by w. Let us assume for our duct elbow radius equal to 100 mm. For this elbow, h by w value is 0.47, so we will select from here nearest value h by w. We will select this column 0.5, it is the nearest value. Then r by w is 0.62, we will see from here r by w 0.6, 0.65. So 0.62 is the nearest, we will select this row. So for our elbow, the fitting loss coefficient value is 0.27. We have one elbow 45-degree. To select the fitting loss coefficient for 45-degree, or if you have any degree, first select the fitting loss coefficient for 90-degree. So h by w value is 0.47 and nearest 0.5, so we select this 0.5 column. Then r by w value is 0.62, so we will select the nearest 0.6 row. So the fitting loss coefficient for 90-degree elbow is 0.27. Then we will select the angle factor for the elbow from this table, and our degree for our elbow is 45, so we will select the angle factor for 45 degree, which is 0.6. Then after multiplication of this 0.27 into 0.6, we will get the coefficient value for 45-degree elbow, which is equal to 0.27 into 0.6 equal to 0.162. To select the fitting loss coefficient for transition piece, if you are doing calculation for exhaust and return air system, then we will select from this table. But if our system is supply air, then we will select the fitting loss coefficient for this transition piece from this table. To select the coefficient values from this table, we should know two values, A0 by A1 ratio and the angle of transition piece. Transition piece in this duct is 815 to 400 by 815 to 300, and flow direction is from bigger size to smaller size. So A1 will be the area of bigger size 815 to 400 millimeter, which is equal to 0.34 meter square, and smaller side area is 0.255 meter square. So A0 by A1 will be equal to 0.75. If we are fabricating our duct as per schema, then for transition piece, for converging the maximum angle we can use as 60 degree. So in our sample calculation, we use the angle 60 degree. A0 by A1 value 0.75. So we'll select nearest value 1 and 0.5. So we'll select 0.5 row. And angle 60 degree, we'll select the column for 60 degree. So for this transition piece, the coefficient value is 0.707. To calculate the pressure drop inside dampers, first you can select the fitting loss coefficient value for this damper from these tables. Then multiplying it by velocity pressure, you can get the pressure drop inside the dampers. For butterfly type dampers, you can select the coefficient value from here, and if for fully open, you can select the angle 0. Similarly, for parallel blade volume control dampers, we use this table, and for fully open we select the value 0 degree and its coefficient is 0.52. Similarly, for opposed blade we will use this table, and for fully open again we will select the coefficient value for 0 degree, which is same 0.52. For fire damper you can select the friction loss coefficient value from here, and its value is 0.19. To calculate the velocity inside the duct, you can use McQuay calculator, or you can find it by using the friction loss chart from ASHRAE. First we will calculate the velocity by McQuay calculator. Our unit is in metric, so we'll select metric. Then airflow is 2000 liter per second. Duct size is 850 into 400. Then you can see the velocity inside the duct is 6.489 meter per second. And the friction loss rate is inside the duct is 0.703 Pascal per meter. For transition piece, we consider the velocity at a smaller cross section. Here smaller cross section is 850 by 300 and airflow inside it is 1500 liter per second. When we apply this value in this calculator, 1500 liter per second, duct size is 850 into 300. Then we found the velocity in this cross section is 6.687 meter per second. This is friction loss chart. Here airflow is liter per second, okay, but the duct size is in round duct diameter. So first we will select the equivalent round diameter for our rectangular duct size. Our duct size is 850 by 400. So let us see 850 here, 800, 900. So we will select both values 800 and 900, and other value is 400. We will select this column. Now we will select both these values for 800 equivalent and 900 equivalent, and by interpolation we will find the equivalent diameter for 850. For 800 rectangular duct size, we have equivalent round diameter value 609, and for 900 we have equivalent round duct diameter 643. So for 850 we will have equivalent round duct diameter value equal to 626. Now we'll confirm by McQuay calculator also. Flow is 2000 liter per second, size 850 by 400, Then you can see the equivalent round duct diameter is 626, same which we found here. Airflow is 2000 liter per second and equivalent round duct diameter value is 626. Here we draw a line for 2000 liter per second, straight vertical line. Then these lines are for round duct diameter. So 400, 500, 630. So we draw a line for 626 millimeter. And at the point of intersection of these two lines, we draw a line parallel to velocity line. You can see this velocity line here. So this velocity value 5 meter per second, 6 meter per second, and 7 meter per second. So the velocity in this duct is 6.5 meter per second. Airflow rate is 2000 liter per second. So we draw a straight line, vertical straight line for airflow 2000 liter per second, and equivalent round duct diameter is 625. So we draw one line for, and this line 630. So we draw from here nearly for 625. So at intersection of these two lines, when we go here for friction loss, it is nearly 0.7 Pascal per meter. For duct size 850 by 400 millimeter, airflow is 2000 liter per second. Velocity inside the duct is 6.5 meter per second and velocity pressure is 25.43. For duct size 850 by 300 millimeter, airflow is 1500 liter per second. Velocity inside the duct is 6.687 meter per second and the velocity pressure is 26.92. For straight duct size 850 by 400 millimeter, we have total length 82 meter and the friction loss rate inside this duct is 0.7 Pascal per meter. Then the total pressure drop inside this duct is 57.4 Pascal. Similarly, for size 850 by 300 millimeter size duct of length 3 meter, the total pressure drop value is 2.7 Pascal. For 90-degree elbow, the friction loss coefficient is 0.27 and the velocity pressure is 25.43. Then the total pressure drop inside this elbow is 6.866 Pascal. Similarly, for 45-degree elbow, the total pressure drop value is 3.69 Pascal. For transition piece, total pressure drop is 1.88 Pascal. When we add all these values, we find the total pressure drop inside the total duct is 72.54 Pascal.